Hello everyone, welcome to today's class. This is teacher Simon taking you through Cambridge International AS and A-Level Chemistry for May, June 2024, paper 1-1, and this is part 2 for questions 25 to 40, which comprises of organic chemistry. Question 25, structure isomerism and stereoisomerism should be taken into account when answering this question. The structure of 3-methylcyclobutene is shown here. And then they are saying a mixture containing all stereoisomers of 3-methylcyclobutene is treated with HBr. This produces a mixture of isomeric bromomethylcyclobutenes. How many stereoisomers does 3-methylcyclobutene have, and how many isomeric bromomethylcyclobutenes are present in the product mixture? Now, when we put HBr, we are going to have here the double bond will go. Okay, so when it goes, we can have bromine here, and then the hydrogen is here. See that? So that means, remember how it is here. You have a carbon, these are two bonds, then one bond, so there is another hydrogen. You see that? So that means if this carbon here receives a hydrogen, then we shall get two hydrogens here. Okay, so I'm leaving it there. There are two hydrogens here. It's the same thing that is here. Okay, now I'm actually going to, let me put off this hydrogen. Okay, let me put off this hydrogen here. It is going to be like that. Then or we can get this one here. When we have the bromine here, then this one takes the hydrogen. Okay, because these two were having the same number of hydrogens here, so it was like symmetrical, so the hydrogen could go on any of them at first. So this is what we are having here. Now, when you look at what we are having here, this one here has gotten a chiral center. Okay, there is a hydrogen here which is silent. So this is a methyl group. This group going this way is different from this one going this way. There is a hydrogen here and then the methyl. So that's a chiral center. And there is also another chiral center. There is also a hydrogen here silent. So that's another chiral center. Then I can write this one, since it's for any chiral center we are having two isomers. So I can say maybe this is 1 and 2. Okay, there are two isomers. Then here we shall have 3 and 4. You see that? Then when we come to this one here, we would have a chiral center here, but because there is a hydrogen here silent, and this is the methyl, but the group that comes off from here is the same group that is going this way. You see? So that means there we are not having a chiral center, and that is one isomer here. So we take it as 1 for that. There will not be 2. The same thing here, there is no chiral center because this group here is the same as this group that is coming off from here. So even that one will be 1. So meaning this one I can have 2 isomers only. Okay, 2 isomers only. If this is the one here, then I will have the second one here. So meaning altogether I'm going to have how many? These are 4, then plus the 2, so we shall have 6 here. Okay, then when we come to 3-methylcyclobutene, there is a chiral center here. Okay, there is a chiral center here, so that means we are having 2 here. It's 1 and 2. So here they are only 2. Okay, they are only 2. And which one is our answer? So this is B. The answer has to be B. Question 26. The diagram shows the structure X which row is correct? They are talking about the number of sigma bonds and then the hybridization. So this one, I can write it like this. This is a triple bond. Then there's a carbon here, there's a double bond, then hydrogen, hydrogen, and then here have a hydrogen. Now for any double bond, that is sp2, okay? And then a triple bond is sp. You see that? Then this is a sigma bond, the bonding between carbon and hydrogen. Even this one is a sigma bond. Now for any double bond, there is one sigma bond and one pi bond. Then here there is one sigma bond. Here there is one sigma bond. And then for any triple bond, there is one sigma bond, but then two pi bonds. So if we try to count the number of sigma bonds, these are 2, 3, 4, 4, then 5, and then 6. So there are 6 sigma bonds. And we see that here, 6, and then sp, and then sp2. So that means our answer is going to be C. Question 27. The diagram shows the skeletal formula of citric acid. What is the molecular formula of citric acid? So there is a carbon here, 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 there is a carbon here. Then here there is a hydrogen. Remember, carbon must have, this is a skeletal formula. The skeletal formula shows carbons are silent, and also the hydrogens which are connected directly on the carbons are also silent. But these hydrogens that are connected to other elements are always shown, okay? Now, that means here there is a hidden hydrogen and then another one here. Those are the ones because carbon must have 4 bonds. Now, let's count how many hydrogens are we seeing. We can see 1 here, 2, 3, 4, 5, and 6. So that means we shall have C6. Then we go to hydrogens. We have 1, 2, 3, 4, then 5, 6, 7, 8. So hydrogens are 8. Then I can write 8 here. Then oxygens, we have 1, 2, 3, 4, 5, 6, 7. Okay, so we shall have 7 oxygens. Which one is it? The answer is A here. The next, number 28, which reaction occurs when ethane and chlorine are mixed in diffused sunlight? This is UV light. And this is a free radical substitution. So our answer must be on these 3. Okay, in the free radical substitution, we have 3 stages. One is initiation, where chlorine, this bond of chlorine is broken down homolytically to form 2 radicals. These ones are highly reactive, then they can attack this molecule of ethane, which is unreactive. So that is what we call propagation. Propagation, here we form more radicals. A molecule reacts with a radical, and then you form more radicals. So if this is the hydrogen here, you bring 1. So this one reacts like this. It contributes this one here. Then this one also breaks homolytically like that. And then you form CH3, CH2. That's another radical formed. Then plus the HCl. And then in termination, this one continues. This one can attack another molecule of ethane. Like that, they continue. Okay. So we are going to have termination. That is where 2 radicals come into contact with each other. So like this is CH3, CH2. It's a radical. And then we also get a chlorine radical here. then they come together, they form the CH3, CH2, Cl. It's a substitution reaction, so one hydrogen has been substituted, you see. So it's a free radical substitution and hydrogen chloride is given off. So that is B here. And then question 29, a molecule of geranium is shown. This is the one. What is formed when geranium is reacted with an excess of cold dilute acidified potassium permanganate? We form diols here, okay? So that means here we shall get an OH. You take away the double bond and then you put OHs. Take away this double bond, then you put an OH and then an OH. So what do we see? It has to be this A here. You can easily see the two OHs and also here, and then the double bond goes. So that is that. Q is either a primary or tertiary hydrogenoalkane. Q undergoes hydrolysis with aqueous sodium hydroxide. The first step in the mechanism of this reaction involves two species reacting together. So if two species are reacting together, that is SN2. Okay, that is SN2, and that is for primary halogenoalkanes. For primary halogenoalkanes, they undergo SN2 because of the weak positive inactive effect that is not capable of stabilizing the formed carbocation. Okay, and then for tertiary halogenoalkanes, these ones undergo SN1. So SN1, you have only one species which is involved in the slow step. You see? So for halogenalkane, if I can use like CH3 and then CH2, like chloroethane, then Cl. Since chlorine is electronegative, it pulls the bonding electrons towards itself, so I can have partially negative, then here partially positive. So that is how a nucleophile can come in. So a nucleophile is rich in electrons, so it donates the electrons to what seems to be an electron deficient, because this one is partially positive. It's like it has lost the electrons because they are coming to the chlorine here because it is electronegative. So then this one can come off, and then you get something like the CH3, CH2, then the OH, and then that comes off, you see. So they are saying which row is correct. Since two species are reacting together, we are looking at primary halogenoalkane, and the behavior of the hydroxide ion here is a nucleophile. Okay, nucleo, this one means from the nucleus. In the nucleus we have protons and neutrons, and protons are positively charged. So what loves phile is to love. So what loves what is positively charged must be full of electrons, because electrons are negatively charged. Must either be negatively charged or full of electrons that it can provide. You see that? So that's why the OH there is a nucleophile. So that means our answer here is B. Then 31, 2-bromopropane is converted to 1,2-dibromopropane in a pathway involving two reactions. So 2-bromopropane, reaction 1 gives us compound X, and then under reaction 2, 1,2-dibromopropane. Now what I can see here, from a mono-bromopropane to a dibromo, that means we need to first make this one an alkene. Okay, so if it's an alkene, we can have, this is CH3, CH, then the Br is here, then CH3. So we shall put here sodium hydroxide in ethanol. This is an elimination reaction. So if I put sodium hydroxide in ethanol, this carbon here, which is holding the bromine, is going to lose it, and then any of these adjacent carbons can lose the hydrogen. So that means we can have an alkene, which is propene, and CH, then CH2. Okay, it doesn't matter whether I put this one here or this way, it is the same. Okay, propene. And then from there, now for me to get 1,2-dibromo, I need to put bromine here. Okay, not hydrogen bromide, because when I put hydrogen bromide, then I'm going to go back to this one here, to bromopropane, because hydrogen will go first to this one here to give us the major product, and then the bromine will come to this. You see that? So meaning here I will get the CH3, CH, Br, and then CH2, Br, 1,2-dibromo propane. So we have to look for heat under reflux with ethanolic sodium hydroxide here, and then HBr, no, it has to be bromine here. So meaning our answer here is D. Question 32. Compound X is a single pure optical isomer. Compound X is heated with an excess of concentrated sulfuric acid. Only one organic product is formed. What is compound X? Now, when you heat with concentrated sulfuric acid, this is a dehydrating agent. So an alcohol is converted to an alkene. Okay, so let's look at the alkenes that are formed here. Now, when you heat this one with concentrated sulfuric acid, this one is going to, this carbon here is going to lose this OH, and then an adjacent carbon is going to lose a hydrogen, and there are two adjacent carbons here. You see that? So that means this one can lose, or this one can lose. So we are going to get these products here, and for them they are going to be two. So one can be this. We get a double bond here. Remember, the OH has gone. Okay, or we can get this one here. So this carbon here loses the OH, I mean the hydrogen, then we get something like that. So these are two. So that means A is off. Okay, then when we go to B, this one can go, and we can have, then we can have a double bond here. Okay, so this carbon here has lost the hydrogen. It has the hydrogen here. Then there is also another carbon here. It is also adjacent to this one, so it can also lose. Okay, so meaning we can have this one here. Let me just copy this. We can have this one here. And by the way, there are methyl groups here. So like that. So those are two. Even B is off. Then let's go to C. When we go to C, we are going to have here, this one can even have more than two. So this OH is going away. Then there is this methyl group here. There's a carbon here. It can lose one of the hydrogens here. So the double bond is there. Okay, so meaning we can have something like this, double bond there, CH2. Because this is skeletal, I'm not going to write CH2 here. Okay, because carbons are silent with the hydrogens that are directly connected to them. And then there is this. Then another one, we can have this carbon that is here can lose a hydrogen which is there. Then we get a double bond there. You see? So meaning we can have this one here, a double bond here, and then there is this methyl, and then that one there. You see? Then there is another one here. Another adjacent carbon to this one is this one here. So it can still lose from here. You see? So meaning I can have, let me just copy this one here, just like this. Let me put it here. This third one here, and there is the OH of course disappeared. Okay, so those are three for C, even C. So that means the answer has to be D. But let's see what is happening here. Now here we are going to have this one here. Of course, now this one will lose the OH. Okay, we'll lose the OH, and then this adjacent carbon here, this is the only adjacent carbon to this one, so it will lose the hydrogen it has, and then we get a double bond there. So meaning we are going to have a double bond here, just like that, and it is the only one organic product, you see. So the answer is D. Then question 33, which reagents could be used to form 2-bromobutane from butane 1O? Now butane 1O is CH3, CH2, 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 OH. Okay, then we want 2-bromobutane. That means it comes from an alkene. Okay, and it has to be yep. So let us first put conc HCl, since here we are having concentrated sulfuric acid. So I can put conc sulfuric acid, not HCl. Okay, conc sulfuric acid. Then I get but1 in CH3, CH2, CH, then double bond CH2. Remember, this one loses the OH, then the adjacent carbon loses a hydrogen. Okay, a molecule of water is lost. Now, from here, if I want 2-bromobutane, I cannot put bromine, because when I put bromine, I'm going to have a bromine here and a bromine here. That will be 1,2-dibromo. You see that? So if I want 2-bromobutane, then I will put HBr, hydrogen bromide, so that a hydrogen attaches to this one. Then you get that carbocation, a stable carbocation here. This one will be plus, then this is CH3, CH2. Then the bromine now can come in here. This will be the stable carbocation because it is secondary. There is positive inductive effect here. So there is the CH3 and then the CH2 here. Okay, they make it stable. So meaning we are going to get the CH3, CH2, CHBr, and then CH3. Okay, so it has to be followed by hydrogen bromide, and therefore the answer becomes a D. Question 34. X is a non-cyclic ketone with, that means it is straight chain, with a single carbonyl group and no other functional groups. Ketone X has the following properties. When ketone X is treated with sodium hydrodoberate, the organic product has the molecular mass 2.3256%, greater than the molecular mass of the ketone X. Ketone X gives a yellow precipitate with alkaline iodine. Now, if it gives a yellow precipitate with alkaline iodine, then that means it must have this group here, the CH3C, the CO. It must have that group to give the yellow precipitate, which is triiodomethane. Okay, now let us get this CH3. Of course, if it is a ketone, that simply implies that we are now going to have a CH3 here, because it must have C, this carbonyl group, and then we have an R and then an R. Okay, so that is the first one there. Then when we reduce this one, okay, we put a reducing agent here, we are going to get a secondary alcohol. So this is CH3, then C, H, CH3, then this one will be OH. Now we have added 2 hydrogens here, so that is 2. What is the MR here? This is 12, 24, 36. Okay, 36, then plus 3, that is 39, plus 3, that is 42, then 42 plus 16, that one gives us 58. So this one is 58. Now we have added 2 hydrogens, so meaning the MR for this one is 60. Okay, so meaning the difference is a 2, so the percentage the percentage here of the organic product to be greater than that of the original ketone, it is going to be, the difference is a 2, then divide by the 58, okay, then times 100. So what do we get there? 2 out of 58, then times 100. This one gives us 3.4. Okay, that is 3.4%. So the ketone is not this one because we are looking for this. Okay, now we can go to another one. We can maintain the CH3 here, this group, then we can add CH2 here, CH3, and then we add 2 hydrogens, remember? So this one will be CH3CH, then OH, then CH2 CH3. So the MR for this one is 12 plus 12, that plus 12 plus 12, that is 48, then plus 5, that is 53, then 56, and 56 plus 16, that one gives us 72. Okay, so MR here is 72. If it is 72, then that means the MR here is 74 because we're having 2 hydrogens there. And of course, the percentage is still going to be, the difference is a 2, then divide by the original value is 72, then times 100. So what do we get here? So just come here and then change this to a 72. And the answer is 2.7 recurring. So 2.7 recurring percent. So even this one is not. Now I can go to the next one. The next one can be CH3. Again, you maintain this group here. Now put a CH2, add another CH2, then CH3, and then you add hydrogen. It will be CH3, COH, then the H here, then we have the CH2, CH2, then CH3. Of course, now every time we are adding a CH2, that is equivalent to 14. So when you add 14 to 72, that one will be 86. Okay, so the MR for this one will be 86. Then you add 2 here, then the MR here becomes 88. So that means the percentage here is going to be, of course, the difference is a 2, then divide by 86, then times what? 100. So what do we get here? I'll just come here and then change this one to 86. And then we can see that 2.3256, okay, 2.3256%. So we are seeing this one matching with this. So that means the ketone is this one here. Now, remember the ketone must maintain this group here. We must have this group here. So another isomer that I can get from here is by shifting this. I use structural isomerism. So this CH3, and then I shift it and I put it on this. That means the hydrogen, one hydrogen that is here will go onto this one. And then what shall we get as the isomer of this? So it is going to be CH3, then C, O here, then C, that is here. Then we are putting a CH3. This one had 2 hydrogens, so I can put 1. Then 1 hydrogen shifts to this one, then it makes it a CH3. And there is no other that we can have, because remember this one must maintain this group here to give a yellow precipitate with alkaline iodine. So these are 2 isomers, this one and this one here. So our answer becomes a B. Question 35, compound Y changes color with acidified potassium dichromate from orange to green. That means oxidation takes place here. Okay, oxidation takes place and then has no effect on failing solution. If it has no effect on failing solution, that means we have no aldehyde, because aldehydes give a positive test with failing solution and Tollens reagent. Okay, then produces an orange precipitate with 2,4-dinitrophenylhydrazine. That means it has a carbonyl group, but in this case it is going to be a ketone, because a ketone gives a negative test with the Tollens reagent. Okay, now what is compound Y? We should look out for a ketone. We can see a ketone here. Okay, but then there is an aldehyde here, so this one is off. Then we can see a ketone here. This is also a ketone, but then it is not oxidized. A ketone cannot be oxidized by acidified potassium dichromate. So even this one is off. Then when we go to C, we can see a ketone and we can see this alcohol, primary alcohol. So the primary alcohol can be oxidized by acidified potassium dichromate. So therefore this one is correct. But then when you look at D, there is an alcohol which can be oxidized by potassium dichromate, but then alcohols don't give a positive test with 2,4-dinitrophenyl hydrazine. Okay, so the answer becomes a C. Question 36. The product of the reaction between propanol and hydrogen cyanide is hydrolyzed under acidic conditions. What is the formula of the final product? First of all, when you have propanol, here CH3, C, then we have this one here. It is like this. So this one is partially positive, and then the oxygen is partially negative. Then hydrogen cyanide. So the cyanide comes in here. It's an addition reaction, and we form what we call hydroxynitriles. So the pi system breaks here when the electrons are being given to this carbon. So we are going to have CH3 here, C, and then O minus here, and then this is Cn, then CH3. Okay, then this one donates the electrons to this hydrogen here in hydrogen cyanide, and then this one gets off, and then you get CH3, C, OH, CH3, and then the Cn. Okay, this is the hydroxynitrile. Okay, then when we hydrolyze this one, we can use a dilute acid. It can be sulfuric acid, but in most cases we use HCl. So when you put dilute HCl, okay, the nitrile here becomes a carboxylic acid. So we shall have CH3, then OH, then here COOH, then CH3. So when the nitrogen comes off here, there's another inorganic product that is formed, which is ammonium chloride. Okay, ammonium chloride. Of course, if you use sulfuric acid, then it will be ammonium sulfate. So that is that. Now, when we look at all of this, the answer becomes how many components do we see here? CH3, CHOH, COOH, but there is no CH3. That means it cannot be A. The answer is actually D, because you can see two CH3s, this one and this one, connected on this carbon that has gotten an OH and then a COOH. You see? So that is that. Question 37. P is a carboxylic acid with the molecular formula C5H10O2. Carboxylic acid P reacts with an excess of lithium aluminum tetrahydrate to form compound Q. That is now a reduction reaction. Okay, because this one is a strong reducing agent and they have said excess, then that means it is going to take it to a primary alcohol. Okay, because this one can reduce the carboxylic acid to an aldehyde, then later to a primary alcohol. But if you use sodium hydrodoborate, that one does not reduce carboxylic acids. Okay, now they are saying which pairs of molecules could be carboxylic acid P and carboxylic and compound Q. So these are 5 carbon atoms. So first identify those ones with 5 carbon atoms. We can see 1, then 4, because these are 3, then 5. That is okay. But then when you come to this one, this is 1, then plus the 3, that is 4. So this one has to be off. Okay, because they are 4 carbon atoms. Then when you go to the next one, this is 4, 5, which is okay. And then here, this is a this is a carbonyl. It's an aldehyde. So this one is off. Remember, it is supposed to take us to a primary alcohol. So that means we shall get it here. CH3, CH3. CH3, there are 3 of them. Then 4, and then 5. So this is a primary alcohol. So our answer has to be 3 only, which is D. Okay, Then let's go to 38. Compound X is treated with an excess of dilute aqueous potassium hydroxide. Okay, and they are saying what is the structure of the organic product. This is what we call alkaline hydrolysis. We have what we call acidic hydrolysis, acid hydrolysis, and then the alkali hydrolysis. So this one is going to be broken down because it is an ester. It is going to be broken down. So you will have this O here, and then this one comes here like that, then here, then here, then here. Now, we would get, remember what was lost here is the water molecule. So we bring back the water molecule. We give the OH, we give the hydrogen to this O here, and then OH to this one here to make it a carboxylic acid. But since we are reacting with potassium hydroxide, this is an hydroxide. Now the hydroxide is going to react with this acid and then it forms a salt. Okay, so the salt, now you remove that hydrogen and then you put the potassium here as a salt. So you can put a minus and then plus there. But since I'm not seeing any potassium in here, I can actually take away the potassium and it remains just like that. It is a salt, and a salt can dissolve in that water. Okay, it's a soluble salt. It's an ionic solid. I mean salt. So that is what we are going to have there. Now, when we try to look around, this is OH that is here, then a CH2 here, which is here, then another CH2 here, which is here, then this carbon here, and then there is this methyl, you see. Then it continues, there's a CH2 here, which is here, then a carbon that is here, and you can see it here. Then, of course, this O and this one here that are here. So meaning our answer is going to be A. Question 39 is coming from polymerization. A section showing 2 repeat units of an addition polymer is shown. What is the identity of the monomer that is produced, that produced this polymer? Now, I can break this one like this, bring this one back, then also here. You continue like that, bring this one here, then this one like this. So what we are going to have is this carbon. Now this one is broken down. Then we shall have a CH3 here. Then there is a Cl here. Then now a double bond has been formed in between these two carbons. So we have CH3 and then CH3 here. Then this one has been broken down. So we have a CH3 here and then a Cl here. Then a double bond has been formed in between. And then we have CH3 and then CH3. Of course, this one is broken. You can see that each carbon has gotten 4 bonds around it. So I can actually write this one smartly, CH3, C, then the Cl here, then a double bond, C, then CH3 here, and then this methyl here becomes a substituent here. So we are seeing but2-ene, okay? But2-ene, then there is a methyl group, and then a chloro. So we are going to have, this is 2-chloro, and then methyl, C and M, which one comes first? It is C. So we shall say 2-chloro. Okay, then 3-methyl. 3-methyl, but2-ene. And which one do you see here? The answer has to be B. Then lastly, question 14. The relative atomic mass of antimony is 121.76. Antimony has 2 isotopes. The mass numbers of the 2 isotopes differ by 2. The isotope with the lower mass number is the more abundant. What is the percentage abundancy of the isotope with the higher mass number? Now, first of all, when we are finding the AR, the relative atomic mass, we sum up the multiplications between the isotopic mass, okay, isotopic mass, then times the relative abundances. The relative abundances. Okay. Now, what we are going to have here, we are going to, they are saying that they differ, the isotopes differ in mass by 2. So if they differ in mass by 2, I can have, this is 121.76. These isotopic masses must be whole numbers, okay? Whole numbers. The relative atomic mass can be, it can be a decimal, but the other ones must be whole numbers. Just like you can have chlorine 35, then we also have chlorine 37, you have bromine 79, you also have bromine 81, okay? They are whole numbers. So we are going to calculate and we see which one can give us these numbers here when they are whole numbers. So let's say we are saying M here. You're supposed to get the isotopic mass, then times the relative abundance. So they say that the masses, the isotope with the lower mass number is the more abundant. And looking at what we are having here, let's pick the 88, okay? So I can have here 88 over 100, okay? Then plus, the other one will be M plus 2, okay? Then times, what is the other percentage? From here, it has to be 12 over 100. So when we multiply all through by 100, we shall get 12176. Then this one is going to be 88M. Open the brackets here, you have 12M, then plus the 24. So meaning 12176, subtract the 24, then this one is equal to 100M. So our M is therefore going to be 12176 minus 24 divided by 100. This one cannot be a whole number. It is going to be a decimal. Let's see. So you have 12176, then minus 24, then out of 100. So it is giving us 121.52. 121.52. So that means we are not having this. And remember, they are telling us to find what is the percentage abundance of the isotope with the higher mass number, which has to be the 12 in this case. But what we have gotten as the value of M is not a whole number. So I cannot have the 12 here, neither can I have the 88. You see that? Now, let's check this other one. If we are having 80, suppose we are having 62 and 38. So let me just copy this whole thing here and then just duplicate it, put it here. So, and then I change this one to the percentages we are going to have. We have 62. They are saying that the isotope with the lower mass is more abundant. So if I'm taking 62 and 38, this one has to be the 62, okay? More abundant with the lower mass, and then this one has to be 38. You see that? Then when we also multiply all through by 100, we get this same thing. And then here we have 62M now. 62. Let me also take off this one here. And this one here, just like that. So I will have 62M, then plus, this will be 38M, then plus 2 times 38, that one will give us 76. So meaning, I'll take the 76 this side, so minus 76, and then our M is going to be 121 minus 76, and then we divide it by 100. So what we get here? So I'll come here and then I change this one to 76, and the answer becomes a 21. This one is a whole number, okay? Since it is a whole number, then that means I can take this one as the relative abundance of the mass, that isotope with the lower mass number as 62, okay? So that means they are saying what is the percentage abundance of the isotope with the higher. Now you might rush to this one because it has given you this, but this is for the lower. But they are asking for the higher, which has to be the 38. Okay, so that means our answer is B. So this has been it for this part of the paper. Thank you so much for watching. May God bless you. If you find the content very helpful, kindly like, share, and even subscribe. See you in the next video.